Today's topic is relativity. There's actually a general relativity and a special relativity. Special relativity came first, and that's what we're talking about today. This was what Albert Einstein came up with in 1905. So he built his theory of relativity on two principles. One is that physics laws are the same in any frame that is not accelerating. So where the acceleration is zero. One example was I was recently on a plane coming back from Amsterdam, and I was going 550 miles an hour. But there was so little turbulence that I couldn't tell if I was moving at all. And that's what relativity is. Also, if a car goes by you at 30 miles an hour, how can the person in the car tell if you're not going by them at 30 miles an hour? And it turns out without friction and without other subtle clues like air or wind, you couldn't tell the difference. The second principle is that light is 3 times 10 to the 8th meters per second. In other words, the speed of light is the same whether observer or source is moving. This one's a little trickier. So say you had a train. I'll just draw this crude train, and someone on the train has a flashlight. So the train is moving at some velocity, could be going pretty fast, past an observer on the track or near the track. When the person turns on the light, people on the train will see that light moving at the speed of light, but the person on the ground will also see it moving at the speed of light. Einstein realized that light could never catch up with other light. Right now I'm walking through space. This room has space, I'm walking through space, but I'm also walking through time. Note that the second hand is moving while I'm moving. It turns out light only travels through space. It doesn't travel through time. So that if you were traveling at the same speed as light, time would stop for you. This leads to something called time dilation. So here's McQuaid, and here's a rocket ship that is about to take off with a student at close to the speed of light. Let's say 99% of the speed of light. The rocket takes off at exactly 9 o'clock a.m. People know that. The people that are watching it take off, they know that because there's an electronic scoreboard light above the school that tells them that it's 9 o'clock. But the student in the rocket, they're not going to see 9 o'clock for a while because that light coming from the scoreboard can't catch up to other light, but it can catch up to the rocket ship. It's just going to take a very long time because the rocket ship is going almost as fast as the light. Eventually, the light does reach the rocket ship and they see that it's 9. Eventually, after a while, a long while, they're going to see that it's 9 o'clock p.m. So, and then eventually they're going to get back to Earth at 9 a.m., a 24-hour trip for them. But when they get back, 100 years will have gone by on Earth because on Earth, time was traveling a lot faster. I'm going to derive the time dilation formula. It's not really that hard to do. We have to imagine a train car, and someone's laying down on the train car. It's like a big freight car. The person has a flashlight right next to their face, and there's a mirror on top of the train car. And as the person moves along in the train car, they flash the light, and so I'll just show it as a beam of light, but it's really going to go up and then come back down. So this same train is about to pass by an observer. First, we'll call the time that it takes for the light to go up and down once. We'll call that the time for the train. But this train is now going to pass the observer. So the observer is standing next to the track, and we'll be able to see this take place as it goes by. And the train's going to be going very fast, almost the speed of light. So this is a bit of an imaginary situation here. The observer would see things slightly different. Because the train is now moving almost as fast as the light, the observer would see the light start in one area and then move to the other area. And we would call this the time of the observer. And they're going to observe it taking longer because it's going a longer distance. So, and we'll just abbreviate T, well, we'll say the time of the train. So this creates a triangle. And bisecting the triangle here is the distance, which is basically the height of the boxcar. And that's C times the train. So D equals VT. Okay, and then this distance here, this longer distance, is the speed of light times the time that the observer sees. And because these are all distances, we can split that in half, and this triangle would represent the one way, either the light going up or the light going down. And so we can just use Pythagorean theorem. So the speed of light times the time of the observer squared equals the speed of light times the time that you would see on the train squared, plus the velocity of the train times the time of the observer squared. C squared equals A squared plus B squared. And if we just go ahead and do some algebra, we end up with this time dilation formula. So that the time that the observer would experience would be the time that the person on the train experiences divided by the square root of 1 minus v squared, that's the speed of the train, over c squared. This is the time dilation formula. So let's apply this on, say, a trip to the next closest star, which is Alpha Centauri. And Alpha Centauri, it's actually a double star, but it's roughly 4 light years away. So that if you could travel as fast as light, it would take you 4 years to do that. Well, let's say we're not traveling at the speed of light, or let's say we're traveling at 0.8 times the speed of light, which would still be the most amazing engineering feat ever. But let's say we're doing that. So the observed time would be, say, 4 years if you were in the train, or close to that. And you would divide that by the square root of 1 minus 0.8 c squared over c squared. And just working with the denominator here, that would be 1 minus 0.64, because the c squareds cancel, or square root of 0.36 in the bottom, for a total time dilation of 0.6. And if we divide that into 4 years, we get 6.67 years, which is what people on Earth would experience while you were taking your 4-year one-way trip. What if the velocity was something really small, like just regular day life, 10 miles an hour? Well, then you would just be dividing by the square root of 1, basically, so the observed time would be the same as the train's time. But what if the train was going at the speed of light? Well, then you would be dividing by the square root of 0, which is undefined, and this is a little bit more than we're getting in today, but through E equals mc squared, that object would turn into pure energy at that speed. So it's unlikely to happen. And then if we were trying to go faster than the speed of light, v was greater than c, well, then you'd be dividing by the square root of a negative number, which would give you an imaginary root, because essentially this can't happen. The speed of light is the speed limit of the universe. So finally, I can rewrite that equation so it's a little more applicable to everyday life. We could say the time of anything moving is equal to the time of what it would take on Earth divided by the square root of 1 minus v squared over c squared. But we can also say the same thing, it turns out, with regards to the mass of an object. The mass of an object moving would be its same as its mass on Earth, not moving or moving with the regular speed on Earth, divided by that same ratio. Make sure we get the square root in there, 1 minus v squared over c squared. So as you approach the speed of light, you get significantly heavier. And then finally, your length also does something, but it's a little bit different. Your length will contract. So your moving length would be your Earth length times that very similar ratio, but it's not in the denominator this time. And I can just give you a little bit of an example of that. I took a bullet train from Tokyo to Sendai, Japan one time, and I was going roughly 250 miles an hour. When you're going at that speed and you pass a stationary train, you go by it so fast that the train appears truncated, it appears shorter. Well, when we were on the track going at 250 miles an hour, we would sometimes pass another train going the other way, also at 250 miles an hour. You had to accept that it was actually a train because you certainly couldn't identify it as such. It was just about a 3-second blur of this gray stuff. The train appeared so truncated that you could never even tell that it was actually a train. Hopefully this gives you a little bit of an idea of relativity and time dilation.